Welcome back, everyone. Good to see you all. I'm going to go ahead and switch over to presentation mode so that I don't end up being the talking head I was at the beginning of the last session. Let's see here. Share screen. Number 2. Okay, how does that look?
Good.
All right, so. All right, welcome back, everyone, to day 2 of What's a Microcontroller with Python and the Microbit. Actually, it doesn't really need to be v2.0, it's just the Microbit. Let's fix that. And also make the screen just a bit larger. View. There. Okay, so today we're going to be focusing primarily on the applications in the 3rd through 5th chapter of the online textbook. Along the way, so in terms of devices, we'll be working with lights, push buttons, and a servo motor. And along the way, we'll be learning about input and output on a microcontroller, because a microcontroller can send or receive either analog or digital signals. Digital being typical on-off 1-0, analog being something that varies within some kind of range. And I'll try to mention it when we get to those. So in terms of we'll also introduce high-low states. And for blinking lights, there's going to be things like frequency, the period, and duty cycle. Those are all words that we'll define today. We're going to be looking at also some of the computer science concepts that are introduced and reinforced in the lessons. And then for the homework, I've got you set up, hopefully, to add a potentiometer to your circuit and do some tests before Friday. Speaking of homework, here we are with the homework from last time. And so how'd it go? Has everybody got their circuits up? Let's see some circuits. I'll show you mine. All right, looking good.
Nice.
Okay.
I'm still working mine out. I've got it maybe halfway done.
Okay. Oh, wow, that's really neat and trimmed and everything, Elaine. Did you shorten some of the wires?
I had some from another. The physics teacher got rid of some old stuff, and I just like it. It's so much neater.
Okay, yeah, it looks very nice and neat. In fact, it looks a lot like the picture. Okay, so there are a couple things, and I think the main thing I want to check, well, let's go through a checklist. First of all, are all these resistors on the left here, these guys, are they red, red, brown, gold? That's first thing to check. Second thing to check is, are these 2 resistors here, are their stripes brown, black, orange, gold? The third thing is just a reminder that we want the longer pins of these LED lights to be on the left side here. We want, like, for example, on this red LED, notice that it's in the same row as this resistor, and then this resistor is on the same row as P15. So that's going to come into play, and I'll talk more about that. Then the last but not least thing, oh yeah, you want the pins coming out of the sides of the case of the push buttons. And then last but not least, I want you to take a real close look at the servo port that you created, and then you plugged a servo on top of this 3-pin header. There's a little, plug on the servo that fits right onto this 3-pin header. So first of all, let's just double check and make sure that your resistor is connected to P16 and that it goes to row 2, the top, which it should share with the topmost pin of the 3-pin header. Next up, on row 5, that's the bottommost pin of the 3-pin header. And we want a wire that's going from row 5 to the blue column. So we want it to be closer to the blue column, the socket in the bus's blue column of sockets. Then the middle pin of the 3-pin header, we want ideally a red wire. So the other one was black. This is a red wire, and we want it to be going from row 4 over to, which it should be the middle pin of the servo header, over to the column, a socket in the column that's closer to the red line on that bus strip. So we don't normally do it in this order. This is to make the course, a little bit more condensed since there's a lot of material to cover. And so we normally do this in more steps. So this particular one is important. When we're all sure that we've got this, and give me a thumbs up, we can move on. Can I get confirmation from everybody that you're sure about your connection? Or, of course, that if you're not sure. Okay. All righty. So what we're going to do today is there's a lot of material that we're going to skip the hands-on part about in order to get through it. So I'll be just talking briefly about every item on this slide. So this is the I'll get back to what this is, but this is mainly the electrical measurements chapter, plus a little bit that we skipped in the board setup and chapter, your first circuit. Okay, because we built up everything for this material, which is the lights, the push buttons, and the servo. And we'll talk more about each of those. So let's start with, I'm going to be going back and forth between these slides. This will be kind of like an intermission. So the first one I want to talk about is what we skipped with the breadboard circuit, because we went straight to connecting our light emitting diodes to a microcontroller so that we can switch them on and off, control the brightness, et cetera. But the other thing you can do, and that I think is important, is to have students just wire up a plain old circuit that doesn't have any programmable intelligence behind it. And this is also where we start introducing the correspondence between a physical circuit, like this LED light emitting diode circuit, and a schematic circuit. And so this carefully has the schematic circuit overlaid above the breadboard so that the positions of all the connections correspond with the parts immediately above them. And so a typical thing we do in each activity is we say, these are the parts you're going to need. And if you've never used that part before, we're going to show you its name, its picture, and its schematic symbol. And so that they're using a larger resistor, a smaller resistor, a light emitting diode, and a wire. And then in this parts area, you'll also often see, oh, well, gee, here's a little preparatory thing we want you to do. You had your probes plugged in up above here. And so we want you, the student, to move them out of the way. And next up, and this is kind of cool, so I'm going to first of all, copy the link and chat it to you. Okay, I got to get this. All right, so there is the first video link if anybody just wants to play it along. I think, though, for this one, it's going to be best to just watch as I sort of fast forward through it. But I'm trying to do that so that at any time, if someone isn't able to follow along, they can catch up. So we're starting here with the empty, except for the power connections breadboard. And then moving forward, we're going to start by taking the black wire and plugging it in on the breadboard. Now, when that happens, the schematic symbol for the connection we just made also appears. So the black wire disappeared from over here and it appears over here. And then here's the schematic symbol for it. And then we go through, and next up is the light emitting diode with the longer pin on the left. And its shorter pin has to be in the same row with that black wire that's connecting to the ground bus, which starts over here, goes to here, and then jumps one more. So all these blue columns are ground, 0 volts. The battery's negative terminal, however you want to think about it. Then the last item is in 2 parts. First part is we plug in one end of the resistor. That's what these peanut-shaped parts with the 4 color bands are resistors, and they resist the flow of current. And notice that we're putting one end in, and we see one end, and then the other end connected to the light emitting diode, and the other end is floated, and we can see that, hey, look, it's in the same row. So yes, they are electrically connected. Then the last step, second to last step, I should say, is connecting the other end of that resistor to the 3 volt bus strip. And then we see the 3.3 volt schematic symbol there. And then the last thing we do is say, okay, here's a magnified version of it so that you can double check your connections. And so this is the kind of thing that the students go through. They don't just kind of build everything up for 3 chapters like we did. They go through step by step, build each thing, test it, and a lot more, learn a lot about it as well. So, let's see, I should continue through here. So the next step is, in this case, we have them check their work since this is the first time they've built an actual circuit. And we talk about the different sockets that we want to see each part plugged into. And then it's a very simple test. You plug in the USB port and the light comes on. So this is something that we skipped. Then there's the how it works part. So after the student has done something, hopefully there's some interest and some motivation to learn a little bit more about it, because students are naturally inquisitive. And so that's the next thing up. When the questions come up, hand raised, I have a question. Well, we try to answer those questions immediately in the how it works section, which immediately follows the build it and test it section. And so here we introduce the light emitting diode in a little bit more detail, talk about how it's a one-way valve for electric current. And if you plug it in backwards, it might not turn on, but otherwise it won't be damaged in any way. And then we talk about the resistor and how it has some color bands that indicate its value and that it's a thing that resists the flow of electric current. And we have to connect that together with the light emitting diode just to make sure that not too much current passes through the light emitting diode, because then it becomes a small piece of plastic with a couple wires sticking out of it that doesn't emit light anymore. Next up, we talk about interpreting those resistor color codes, since they're a little bit mysterious. They're actually quite simple. If you have the first two colors or the first two digits in the resistor's resistance value, that is measured in ohms with the symbol omega, and red corresponds with the number 2. So the first two digits in the value are 2, 2, because the first two stripes are red. The third stripe is the number of zeros to add, or if you're in higher level classes, the power of 10, the power that you raise 10 to. But in simple terms, it's just the number of zeros to add on. Since we have brown, which is the number 1, we add 1 0 to those first two digits to get our 220 ohms value. Then the last stripe is the gold stripe, which is an indicator of how precisely you can expect the actual resistance value to match what those stripes are telling you. So with gold, that means it's a plus or minus 5% resistor. So it's not going to be exactly 220 ohms, but it'll be 220 ohms plus or minus 5%. We also talk about how, when they plugged in the USB supply, it's like connecting a battery to your circuit, and how the electrons flow out of a battery's negative terminal through the light emitting diode through the resistor to recombine with positively charged chemicals inside the battery. Also, we show that for reasons not entirely known to me, although there are stories about Ben Franklin not knowing that whether the positive or negative charges were the mobile ones back in the day when he was first doing research on electricity. The schematics show current traveling through a circuit as a value that's going from the positive terminal through the negative terminal, even though physically the electrons are going in the opposite direction. All right. Then the last thing we do with the students here is say, hey, try a larger resistor value, which is why at the very beginning there was a 1000 ohm resistor along with a 220 ohm resistor in your parts, so that once you get to here, you can try that out. And then there's always some review and practice at the end, self-check. And in this case, just exercises, but we normally have questions, exercises, and projects. And then finally, there are solutions provided to whatever we have published here. And then we make an extra set of questions, exercises, and projects and solutions available to you, the teachers. And we'll talk about that closer to the end of this session. Next up, we get to the electrical measurements chapter. There's a fairly significant amount of material here. I'm just going to talk about voltage measurements as quickly as I can, and then we'll go into doing some applications with the light. But these are things that preceded what we're going to be doing with the light today. So the first up is a repeat on building your light circuit. And then here, we have the light circuit, but we're using the probes. The student is going to be using the probes, but instead of measuring continuity, this time the student is going to measure the voltage across each element in that circuit. Copy link address, paste it into the chat. There we go. And I'm going to open this video clip and just briefly say that, all right, so we're starting off with the wires measuring the same row of sockets here, the voltmeter probes. So we're using this as a voltmeter as opposed to a continuity tester. And in the cyboscope, it's showing 0 volts. Now, when the students check the voltage across the whole circuit, they see that it's about 3.3 volts. They're measuring from the 3 volt terminal here to the 0 volt or ground terminal right there. Then the checklist instructions in the activity guides them through, all right, now measure the voltage across just the resistor and record it. Oh, okay, it's 1.2 volts. Okay, next, measure the voltage across the light emitting diode. Ah, that's 2.06 volts. And spoiler alert, those two add up to 3.26 volts. And that's kind of a summary of the hands-on part that they do. Next, because the questions are coming up about how it works, and actually how it works and did you know are also places where we get the curricular checkboxes checked off. And in electronics, an important curricular checkbox is something called Kirchhoff's voltage law, and it states that if you increase, but if you have a loop of parts connected together end to end, which we do in this circuit, the sum of the number of voltage increases, like that across the battery, is equal to the sum of the voltage decreases, like the ones across the resistor and light emitting diode when added up. And so that's Kirchhoff's law. And then we have them try it with a 1000 ohm resistor and repeat the measurements. They're not very different, but they're slightly different, but they still should add up to the total voltage across the circuit. Okay, so that is, and then here is a more typical end of chapter material where we've got our self-check, where we think about the skills and concepts that were introduced. Then there are questions, exercises, and projects. And again, this is half of them. The other half is in the teacher's material that we'll be spelunking through on Friday, and actually making sure that we have access to between now and then. Then we'll go to some fun hands-on activity stuff. You ready, everyone? I see some clapping. All right. So the first part here is introducing one of the lights. Now, don't worry. In all the pictures, it's showing a green light connected to P14. If you look at your circuit, you're going to have a yellow light connected to P14. That is okay. So in the introductory area, we talk about why is this relevant? Where do you see it? And in this case, indicator lights, they're ubiquitous. They're in every contraption and device that we use on a day-to-day basis. My microphone is telling me something with its indicator light, and I can see some on my monitor, and so on and so forth. This one is basically the circuit that you're starting with. So this is saying, all right, where you left off is with this circuit, but we want you to take this resistor that used to be connected to that plus rail, that 3.3 volt column, and disconnect the end that was in 3.3 volts and connect it to P14. Now, again, and all points bulletin, everybody, do not pull apart your circuit. We want to leave all the stuff that you've got on your circuit on, because we're going to try it all today. This is just, an earlier point. And as we go through further activities and chapters, you'll see more parts of the master circuit that you have built right now. In terms of script and tests, let's do our first test by plugging in well, actually, I shouldn't copy that first. I'll give you the link to the Python editor. Okay, so here is the link to open a new tab and paste that in, so you've got your Python editor going. And so that's python.microbit.org. And then I'm going to copy the script, and we'll just, I'll chat it to you, and then you can paste it into your editor. So basically like this, I'll go ahead and shade everything that opened with the editor, and then paste in the LED blink script. And then hit connect. Remember, when you hit connect, it's going to offer you a list of microbits connected to the computer. You'll only have one. Select it, then hit connect, then flash. And then after it's done flashing, look down at your board and hopefully you will see a flashing yellow light. Mine is taking a little longer because I apparently was using a different programming tool, but now nothing at all is happening. So I have a bad connection. How about you guys? Does anybody want to hold up their, oh, beautiful. I love that.
Aw.
So everybody but me has their blinking light. That's okay. I've done it a few times, so I know what it's like. So we'll move on. Okay, so next up is, and so this is the step-by-step. Every time there's a step-by-step. So notice that in the tutorial, we've got a link to the python.microbit.org editor, and then steps of all those things in text to the different buttons to click in the editor and what to type in. And by the way, really for best results, I recommend having the students, whenever their screen is wide enough, tile it like this, so that on the left side, they're looking at their code, and on the right side, or vice versa. I actually do it like this, and I go through programming tutorials a lot. Every year I'm learning some new language or API. And so it's actually best if you can get them to do it, to hand type it in. Not all of them will, because it's text that they can copy and paste. But guess what? In the try this section, at the end of the next section, there is a little area here where there's a screen capture. So they can't type that in, and it, let's say, encourages them to type it in themselves. And you can further encourage them by requiring credit by submitting it. So in this case, all we're doing is making a small change, which is, instead of having it blink infinitely, we're going to have it blink 10 times. So we'll modify it to 4n in range of 0, 10. By the way, in range is inclusive of 0 and exclusive of 10. So it's going to count up to from 0 through 9 before it bails out on the loop and does nothing afterwards. So try making that modification yourself. And let's make sure that that it goes ahead and does the that's the funniest thing. Oh, there's the error. One of my wires came undone. Oh, there's the first error. What else is there? Okay, so did we all get 10 blinks out of that? Excellent. Next up, there's some theory, because this is the did you know section that follows the try one small thing after seeing the how it works explanation. Oh, and I forgot to show you the how it works. It's kind of cool. This is a good one to talk about in class. So copy link, paste it in, and open. Okay, so with this one, all right, there's a lot going on here. First, as I move the play control, the light is currently off. It's because we just hit the while true statement. And the immediate next thing that happens after while true, which the microbit just tells itself, okay, I need to do everything below and indented from that statement over and over again. So the first thing that happens is we get to pin 14.write digital with a 1 in parentheses. And what that 1 does is it causes the microbit internally to connect its P14 plated piece of its edge to 3.3 volts. And that plated piece of the edge is connected inside this adapter. So it makes it here to the P14. Well, that's 3.3 volts, just like when we plugged it, built it manually, built the circuit manually and had it connected in one of the 3-volt sockets. So now we have a light that is on. And then the sleep 2500 is going to leave it in that state for 2500 milliseconds or 2 seconds. After that, the next thing that happens is pin 14.write digital of 0. Now we see that the light turned off. Why did the light turn off? Well, it's because inside the microbit, it connected P14 now to ground. And we have ground on one side here, 0 volts. We have ground on the other side here, 0 volts. There's no electrical pressure across the LED circuit, no current flows through, and so no light is on. And it does that for another 2.5 seconds. It waits for 2.5 seconds. Then it goes back to while true, and it goes through these over and over again, just like that. And that is why we have that blinking action. And this one is actually better in the GIF because it just keeps repeating over and over again. And I always call it GIF, even though I've been told several times that the proper pronunciation is GIF. So then here's another try this. See how, oh no, that's the try this we just did. Then we go to the theory of on-off signals. How long is the period? Well, that's the high and the low time added together. Then there's a calculation example. What is frequency? Well, that's actually 1 over the period. In more layperson's terms, it's just the rate at which something turns on and off or repeats itself. And then we go through some math on, hey, the frequency, the period is this. What's the frequency? Well, we use the equations, and then we go from period to frequency, and then from frequency to period as an example. And then we introduce something called duty cycle, which is the amount of time that the light is on in relation to the amount of time it's on and off. And that's the duty cycle. And that's another important thing. And we go through some calculations of that. And then in the your turn, we actually try this out. Now, I'm not going to ask you to type this in, but the students will have to type this in. Let's see, where is the slideshow? Here it is. And so we'll try duty cycle. And I think that this, okay, this, trying to remember what this does. It says blink at varying rates, and I'm looking at the code. And it looks like we're just blinking at two different frequencies. Well, let's find out. Okay, so this is, did you know, this is on-off signals. Okay, so this is going to be a new way. Instead of pasting the code in, I'm going to have you download a hex file and open it and then load it that way. So here we are with on-off signals. Okay, so I'm going to give you a link that takes you to a page that looks like this. And then all you have to do is download the hex file. And it'll briefly open in a new window, and then your hex file will appear. And then you'll take that hex file and drag it and drop it into your editor. And then you'll have the entire code example. and we can all find out what I forgot I wrote about there. So here is the link, and we'll have us all try it out and find out together what that particular code example is doing. Flash. So remember, click download and then drag your downloaded hex file and drop it onto your editor, then hit flash. Okay, so we're changing the frequency from low to high and then back to low, and we're doing it a little bit at a time each time through the loop. So what we want to see is it blinks slowly and then gets faster, 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 really fast, then slows down again, and then faster again and slower again. And we are doing that by basically taking the time, and to make it larger, we're multiplying a variable named scale by 1.3. So we're making it a little bit larger each time, and then we're recalculating time based on that. And so we're making time a little bit larger each time through until it gets to a whole 2-second amount of time between turning it on and off. Then it says, okay, we need to now start multiplying by a smaller value so that time starts getting smaller again. So that is how that program works, and we go into more detail in the activity itself. So, but this is at the point where we want the student to be trying kind of hard because this is the very end of the chapter example. And then, of course, the same old review and practice. And as you can see, we're getting more and more material as there's more to, as we start adding in more theory, and then we have the solutions, or rather half of them. Okay, brightness is kind of fun. Let's try, and you've already got your circuit built and ready to go. So let's try a few different brightnesses. Pardon me. Well, Stephanie, are you recording? Did we? Yeah, we did start recording. Excellent. Okay. Now, was I talking the whole time but not sharing my screen? And nobody told me?
Rebecca's nodding yes.
Yeah. Oh boy.
Well, Kip has his hand up, so.
I couldn't see that. Okay. Well, you got the code, and was everybody able to observe that slowly blinking, then more rapidly blinking? Excellent. Thanks for your patience with my absent-minded Zoom instructing.
Andy, another question for you.
Yeah.
Can we look at that print command in that last set of code?
Yes, right here. Oh, that's a really good question. Thanks for asking. So let's try this. If you have the program running and you're connected, there's an open serial button. And you can actually see how the time between turning the LED on and or off varies as the script is executing. And this is the serial terminal. and this is where print statements go. So display.show is going to be shown on the LED matrix display on the microbit, but print will show up here. Now, another cool thing that shows up here is if you've made a mistake in your code, like instead of while true, I accidentally, my cat stepped on the keyboard and it's while true. So if we flash that, we'll end up seeing a very slowly scrolling error on the LED matrix display of the microbit. Okay, I have to remember to So here it is scrolling across the microbit. It's really difficult to read. And so what we do instead, remember to share screen. So what we can do instead is just hit that open serial button and possibly hit the reset button. And then it says the line number that the arrow is on and the kind of error that it is and actually what caused the error. Now, it doesn't always do every single one of those, but this is a nice example of you know, what you'll see in the best possible scenario, I think. And so we can run and say, okay, what's going on line 22? Hold on, open serial. Why is it saying line 22? Close serial. It's probably because that's the last point before it comes back up to while true. That's an unfortunate example, actually. But then after correcting it, because it did at least call out that while true was misspelled. So it will get you much more quickly to a solution of the problem, and it's much easier to read than the matrix display on the microbit. And I am screen sharing, good. Okay. Then there's add a light, which I'm going to, there's set brightness. Set brightness is fun. Now the format and is mostly similar. I think the more about A to D has a little bit of information, but oh yeah, that's right. I do want to just run the basic script so we can talk about setting brightness. Okay, so now we are going to be going back to, instead of downloading a hex, I'll just paste it into the chat again. Okay, paste. There we go. So try that out. That should start with a very dim brightness on that yellow light, then a little brighter still, and then it'll end with maximum brightness before repeating the pattern. So it should be 4 increasing levels of brightness before starting over again. Is that what we've all got? Okay. I'm going to speed things up here. The students will see it in the student materials, just like the rest of the things I've showed you. I'm just going to quickly say that 128 is 1/8 of full brightness. 256 is 1/4 of full brightness. 512 is 1/2. And then 1023 is maximum brightness when you're using the right analog method of pin 14. Everybody okay with that? All righty. As always, feel free to jump in if you want to unmute yourself and ask a question. So that's basically what the how it works said. One thing I would like to add is that basically the analog world has an infinite number of possible values in one brightness. But our eyes have difficulty seeing a difference between, say, 514 and 515. If those were, if we ran a script that did a brightness of 514 and then a brightness of 515, it'd be really hard to tell. But if you have really good equipment and you're measuring it, you would see a significant jump, whereas in reality, there's a whole continuum of brightnesses just between those two levels. And that's a distinction of analog versus digital. These are digital values. Well, these are still really digital values, but they're trying to convey that, you know, in the analog world, things have a continuum of values as they go from low to high, high to low, et cetera. So then there's add a light. I'll go ahead and just give you the script for this. There's a lot to cover, so I'm going to start skipping more lightly through some of these chat, paste. Okay, so try that one out. And that should give us 2 lights. Huh. Yeah, it looks like my my green light is messed up too, so I can't show you that. Let's see. Oh no, for some reason I'm still on the there we go.
Are you supposed to be screen sharing?
Flash. Well, thank you, Stephanie. At this point, I was intentionally not screen sharing. Okay, so we have something like that, where the, yeah, where both lights are blinking on and off. So could I have you guys give me a hypothesis of how to make them blink alternately instead? Somebody unmute and say it. Ah, you guys are so quiet. Okay, so the try this after the how it works says, okay, take that 1 on line 7 and change it to 0, and take that 0 on line 10 and change it to 1. And this is where I need to be re-screen shared. Okay, so again,
I actually moved the code around and added some more delays and got the blinking.
Oh, cool. That works too. Let's see here. I want to share the screen. There we go. All right, so the code started like this. And the try this says, hey, try changing that 1 on line 7 to a 0, and try changing that 0 on line 10 to a 1, and then reflash the code and observe the result. And so that's alternate lights. And then there's also a blink sequence that's introduced in the your turn. The try this was alternate, and then the blink sequence was your turn. Okay, computer science wise, there's an introduction to lists. I don't want to spend a lot. I'll try to explain it briefly. Let's see here.
Screen share.
Oh, thank you. Okay, so let's talk briefly about lists. So instead of an electronics concept, this is a computer science, or a programming concept. And let's see, so did I pasted you in the wrong thing. Here, if you want to view it, as a link to the actual video. And So the important thing is we have this list that's been created here. This can be elements, these happen to be 3 strings, but you can also have things like integers or floating points or Boolean true false values. But in this case, CList of 0 with square brackets is green. CList of 1 is yellow and CList of 2 is red. Okay, and then as we're running through the script here, setting index to 0 means that index stores the value 0. That's what the little thought bubble is trying to say. Okay, then we get to while true. Now, index is 0, which means that it's going to jump up to CList. So see how it says CList of index? Well, index is 0, so it'll jump up to CList. It'll grab the CList of 0th element, which is green, and then basically put that where you see this piece of code so that now CList of 0 is really green. Then it's going to print it and we'll see that it's green. It'll sleep for a second and then increase the index by 1. So now the index is 1 and it says, hey, is that higher than the end of my list? Nope. So since that's false, we're going to skip back up and not do any of that stuff that's below and indented. The index equals 0 and print. So then it goes through again. This time CList is 1, so it grabs yellow and we display yellow. And so this is a way of introducing how a list, and some of you may be familiar with arrays and say C, Java, JavaScript, BASIC. A list is very similar, but it does have some extra uses, and there are some nuances of why a list is different from an array, but that would be an advanced class. And so we talk about data types. So this is more computer science stuff. Now, after doing that computer science intro, what we're going to try to do is reinforce it here with all right, let's set up a sequence using a list that affects your lights. And in this case, we have a list of different pin numbers that can be turned on and off. So there is the script pasted into the chat. Try pasting that into your editor and running it. Flash. And what we should have is something like that. So that's the use of a list. Now there's a lot of, not a lot, but there are several other things we do with lists. But in the interest of time, I'm going to leave that to you guys to do on your own when you're preparing to teach, because really, this is at least 40 hours of class material. And so in 4.5 hours, the main thing I'm trying to cover is just anything that you might end up potentially tripping over. And most of that has to do with how to use the editor, how to use the materials. And so I'm trying to give good examples of what the students are going to be presented with at various points in each lesson / activity, and what the elements of the activities are, etc. Now, there's a blinking light with a voltmeter. I'm going to skip this for now. I'll just give you a quick look at what it looks like. You can download Blink with Voltmeter, and what it will show you is that when the microbit turns the light on, we see about 2.6 volts, and when it turns it off, we see about 0 volts. Okay, and then there's also a really cool thing where we measure it with an oscilloscope. And that looks like this. This is just too cool. We've got to do it. No, I'm gonna try to pick up later where there's push button and blinking light on the oscilloscope if time permits. So these are or how about this? I'll just demo it quickly. LED, so we can download this. Okay, so I downloaded the hex file. Then go over to the Python editor and darn it. Okay, drag it in. So this is the script. We'll flash it. And then this time, since we're using the cyberscope, we'll disconnect it, go to cyberscope.parallax.com, and then hit connect here. Make sure to choose the right one. And so, oh, I forgot to connect my alligator clip probes, and I'll show you that in a second. So it's very similar to what you've seen earlier. Okay, so here we can actually see the high-low signals of the light turning on and off in the oscilloscope. And you can also, the your turn of this has you look closer. Now it's kind of hard to figure out what's going on here because we just zoomed in on everything, but we see it replotting itself and it's moving across the screen and all that. And for that, oscilloscopes have a thing called a trigger, which is a pair of crosshairs. And in this case, it's going to line up the rising edge of the signal with that trigger. And so now everything's staying still and we can say, oh, look at that. It's the signal is high for just a little over half a second here, from 1,000 milliseconds to 500. Then it's low for just over half a second and high for just over half a second. And that high isn't really 3.3 volts. It's more like 2.6 something volts. Okay. And so while we're here, just try to race through this because I'm watching the time. The voltmeter looks like this. Script and tests, download it. Okay, so here's the script. And basically there's just a statement added after each change of the pin in this case that says, hey, display it in the Cyberscope voltmeter. And so we'll go ahead and load that. So that's flash. Make sure to disconnect before going back over to the Cyberscope. Whoopsie, connect. It automatically switched over already. So you can see that when the light's off, it's 0 volts. When the light's on, it's 2.7 volts. And then one last item about that is that the circuit that we're doing looks like this. So we're basically putting, the probes are connected to those same 2 3-pin headers on the bottom, and we're connecting the black probe to the ground column, and then the red probe to the LED connected to P13 to get all that done. Okay, what's up next? A little bit more in electrical measurements. So there is measurement, resistance measurements. Now, for resistance measurements, you actually have to build a resistance measuring circuit. And so this MP4 shows how to build, no, this MP4 is showing how to measure the circuit. this MP4 is showing how to build the circuit. And I'm going to just open it quickly. I'm running out of time, so I'm going to try to go quickly. I don't think we need to dwell on this very long. It's just, this is a close-up of the resistance meter circuit. And then afterwards, you go ahead and clip your probes to a different pair of 3-pin headers that are added as part of that resistance meter circuit. And then we put the resistors in. Okay, so there's a close-up of the probes connected at the 3-pin headers, and then that's it. So now we have our resistance meter circuit, and then after that, running the script and using the cyboscope, what we do is we take a resistor and we stick it in the same row as the probes across the little valley. And then in the cyboscope, we can see in this case that it was 218 ohms instead of that 220 ohms, because there was, again, that plus or minus error. So, and then there's also measurement units, which are very important. And so this is more curriculum stuff. So here's an example of SI units. And we introduce it as, hey, you know, you might see a resistor, instead of saying 1,000 ohms, you might see it say 1 kilo ohm. And so what is that ohm symbol? And what is that lowercase k? And this goes through a whole lot of material that talks about, okay, we've got a metric prefix K for kilo. Well, first it introduces each one and tells you, K is kilo, capital M is mega, et cetera. And then we go through some examples of, hey, if you have a K, that's really times 1,000. Or if you have a lowercase m, that's really times 0.001. And then we go to, all right, let's write a script that can make those conversions for us, so that if we start with a K, we'll have times 1,000. If we start with an M, we'll have 10 to the 6th, and so on. Let's see here. Now, an example of converting the other direction, of converting a quantity to a favorable metric prefix, we have to figure out the, what a favorable metric prefix is going to be. So like if we start with 38,000, well, those 3 zeros can basically be a K. And it shows step by step how to do that. And then it also shows some Blackboard stuff, basically how you'd teach it on a Blackboard, but right there in the web page. And then after that, there's actually a script. So we approach it from, theory, hand calculations, and then script. Measuring current is a different circuit yet again from measuring voltage. And in this case, and so we're going to use the cyboscope as an ammeter. And basically, the way it works with setting up your ammeter is you add a very small resistor in that particular spot that it just magnified. Then you actually have to break apart the circuit. And then what you're doing is you're inserting the ammeter in the circuit so that it's in series with it right here. And that way the electrons flow through the ammeter and the microbit measures it and then makes it to ground. And so, so that's how an ammeter is used. And I know that was very quick, but it is, very meticulous and step-by-step with the full video support. So I'm confident that you guys can do that when you're ready. Finally, we do Ohm's law. Now, Ohm's law is basically the official one is I equals V over R, and then you can use algebra to reorganize it in any of these three ways. And the reason I saved it for last here is because at this point you can say, you know, wasn't that kind of a lot of work to do the ammeter measurement? Well, guess what? You can instead measure volts with ohms and then use Ohm's law to say, well, I know what the voltage was and what the resistance is. And so now I'll calculate the current. And so it shows how to probe a resistor and then use the measured voltage and some calculations to figure out the current. And as we go through this, you do it by hand, you solve some algebra problems, and then even write a script to solve for, you know, current if you know resistance and voltage. How are we doing? Chris, I see you saying something, but
I just think that that's a cool use of this right here. I like this.
Oh, fantastic. Okay. Yeah. So it takes a while. I wish I had more than 4.5 hours for you all, but you know, it's all pretty well supported. So I think that having the students go through it on their own, or you know, even if you have to try to just stay a few activities ahead of your students when you're implementing it, it should work out fine. And so that's why I'm kind of breezing through that part. All right, so now let's go to push buttons. And so we'll test out our push buttons here. And again, there's time. So the push button is the same. We start with one push button. We learn some things, we try some things, we write some scripts, we modify some scripts. And so I'm just going to jump into push buttons on adding the second push button circuit, since we have it all built up and all we really need to do is test and make sure both push buttons work. So let me make sure that this is the right one. Yes. All right, so what we're going to do with this one is I need to disconnect the cyboscope. I'll paste this in a second. I'd like everybody to just watch. So this is testing both push buttons. And again, this is very step-by-step. So I'm jumping in 2/3 of the way through the chapter here. And that's because we have 20 minutes left. All right, so what this is going to let us do is check to make sure that the microbit can tell that we're pressing each push button. So I'm going to go ahead and load this in. And after you've loaded it, using the flash button, the next thing to do is open serial, because this is using print statements. Okay, so see how on mine it says state 9 equals 0? That's the push button connected to P9 is not pressed. State 6 equals 0. That's the push button connected to P6. That's not pressed either. Now, when I hold down the push button connected to P6, notice that state 6 starts showing me once. Likewise, if I press the button connected to P9, state 9 shows me a 1. Okay, so now that you've seen that, I'd like you all to try it. Copy, chat. Where's chat? Paste. Okay, so there's the next one for you to try out. So interesting statistics exercise would be to try to figure out the likelihood of how many students in a classroom. Awesome. Elaine, thumbs up. Chris, okay, you guys are doing great. How about you, Kip? Still working on it? Oh, nice. All right. So if anybody does not have a push button working and wants some troubleshooting help, we can stop. Just unmute yourself and let me know. Otherwise, we will move on. Let's have some fun with the Cyberscope. Okay, I'm going to paste this link into you. Okay, now this is one of those pages where you're going to see the download, and you want to open that download in a new tab, and it's actually going to download a hex file. Whoa. Okay, let me try this again. I'm going to click the download. It opens a hex file. Oh, that's right. Okay, heads up, everybody.
It says right click.
Yes, right click. It's important to follow the instructions. I only write them. I never follow them, just so you know. Anyway, yeah, right click and select Save Link As, please, everyone. Thank you, Stephanie, my editor. And then once you've downloaded that, go ahead and drag it and drop it onto your python.microbit.org editor. And then flash it and hit disconnect. So first let it flash and then hit disconnect. And then we need to go to cyberscope.parallax.com. I'll paste that in a second. I don't know if maybe I closed it. The Cyberscope link is on its way, or it's actually also in the instructions here on the page. Right here, you can just open it in a new tab. Not sure what happened there. Oh, okay. Python.microbit.org, yeah. And Cyberscope. Here is Cyberscope, the link to Cyberscope. And this is what it looks like when you get there. And then this is what it'll look like when you hit connect. So all it's going to be doing, oh, you know what? I'm getting ahead of myself. I'm getting us ahead of ourselves, rather. There's some connection stuff. After you've got your Cyberscope ready, I'll show you what to do with the alligator clips. Hopefully everybody can see that. Okay, so remember, feel free to unmute yourself and let me know, if you would, when you've either got it running in the Cyberscope or are stuck. When you have it, if you think you have it running in the Cyberscope, you'll want to press the push button connected to P6, the lower of the two.
Okay, I get a big spike or a big.
Okay, so what to expect once you've got that here. I'll paste in this page for those of you who are still working on the schematic. Here is a link to the schematic I had you building from. And then, let's see, was that Elaine? So Elaine, you're wondering what you're going to see. And for that, I need to get back over to the Cyberscope. All right, so you know what? I was watching you guys do it and I didn't do it. Connect. Okay, so what I have is two kind of low voltages being plotted across the screen. And then when I press and hold on the lower push button, what we want to see is the LED plotted going high and low, and the level of the push button going from the bottom of the display to the top of the display. So this red trace is the light turning on and off. And you can also change the time per division so that you can see it a little bit better. And then when you let go of the push button, everything goes back down to 0. And what the activity does is it has the students try to press the push button for long enough so that they just see 6 blinks. 1, 2, 3, 4, 5, 6, boom. There we go. Another thing that we do is use that trigger feature again and set it so that it's looking at channel 2, which is the red trace, or no. Yeah, we want it on channel 0, which is the black trace, because that way, what it does after a few seconds wait is, so I just press the button for a little while and let go. And it takes a while for the oscilloscope to collect enough points, but eventually it will go ahead and align that with the, it's taking a little longer than it should. Let me make sure that I'm doing this right. That's a pretty crazy drawing right there. There we go. That looks a little bit better. I made some small adjustments to the to this software last week, and I am possibly seeing a little error to my adjustments. But overall, what this is plotting, if we look at this this black line, this is the push button, and it was at 0 until I pressed and held it. While I was pressing and holding it, the light blinked 1, 2, 3, 4, 5, 6, 7 times. So your two key things to be experimenting with are the time per division and then the trigger settings. You know, another thing is this may be some kind of loose connection that I've got.
I think it's because we're watching.
Yes, of course. I forget whether we call that a Heisenbug or a, forget what the two names for the bugs that are related to observation are. Okay, how's it going? Did I lose all of you to the Cyberscope? I think 500 milliseconds per division is a good time range for being able to see the light going on and off while you hold the button, and for being able to see the button go high and low. So the button is the black trace, and the light is the red trace. And here, by the way, is a picture of one of the things we try to get the students to do is to, at 1000 milliseconds per division and the trigger set to none, they try to get 6 blinks out of the light so that they can see while they're holding the button and seeing the light blink. And then the trigger settings that I showed you is in the in either the your turn or the try this. But so first and most importantly, see if you can get this. So let's see here, where'd my cyberscope go? Okay, so I have my goal here on the right. I have my cyberscope plotting away on the left. And the first thing I'm going to do is try to notice, it's very subtle, but you can kind of see where the points are getting updated along the bottom of the screen. Oh, but also I'm not following the instructions very well because the instructions have you set it to 1000 milliseconds per division, which is these little squares. Each one is 1000 milliseconds or 1 second wide, which means that we're seeing 10 seconds worth of plot here. One, two, three, four, five, six. So there we go, except for that 7. Close enough. So were you guys able to do with that? Okay, good. Can I hear some opinions, some discussion? Are you guys okay? I realize we just sort of jumped into this and it might be a little bit overwhelming. On the positive side, it's the minimum for an oscilloscope is usually about $400, but we're using a $20 microbit, so that's kind of a good way to get better training into lower classroom levels. So despite all the racing I did, we didn't quite make it to servo control, but let's just stay a little bit over time if you guys can hang with me. And we'll just make sure that all our servos are working. Is that okay?
Can I ask a question real quick?
Yes, please.
Are we going to put off looking at the educator material then?
Oh, that's just a quick slide, so I'll hit that.
Okay.
Okay. For the servo, normally what we do is the servo is equally step by step. Actually, the first step is connecting and testing the battery pack. And I should at least mention here that for the battery pack, just a reminder that when you plug it in, the red wire should be on the left, not on the right as it's shown here. And we actually do a voltage test to see what the battery pack voltage is. That's what this activity is about. And then after talking about the battery pack and voltage tests, we go to the servo and say, hey, this is a servo. It has this horn that can rotate to different positions in a 180-degree range. And you know, we're going to actually take that horn and remove it and rotate it all the way to the right, then take the horn off and put it on so that it's facing directly right. So you want to rotate it to its all the way clockwise position, then remove the horn and then push it back down on the output shaft so that it's pointing to the right. We actually don't need to do that right now. And so here again is double checking your wiring and then plugging the servo on top of it. And then here we are done. And so the next thing is script and tests. And so I'll go ahead and paste in this test script and we'll give it a try. And folks, this would be the time to grab your AA, AAA batteries and put them in the battery pack. And then run this script and observe what your servo does. The batteries may still be in that clear plastic bag, which is where the battery pack was. So what you would expect to see is I'm holding the servo up top here, and this script basically, now I have already pulled the white horn off and then put it, I've already done that little part that I'm suggesting you skip for now. And so, but after following those instructions of turning it until you feel the clockwise limit and then pulling the horn up and off and putting it down so that it faces right, if you do that before running the script, you will essentially see the script point to 0 degrees. So there's 180. There's 0, roughly. 45. 90. And 180. A servo is the thing that they put in model airplanes and boats and et cetera that keeps those airplane flaps at a certain level when you're radio controlled flying it, or keeps the boat rudder at a certain angle to make the boat turn, things like that. That's what hobby servos are used for. All right. Pretty interesting stuff. We'll try a few more things with the servo next time. How about that? Because there's a lot of cool applications. You can tilt your microbit and have it move the servo around, and we'll put a potentiometer on and hopefully do a little bit with that too. Potentiometer is a little knob that you can twist, and you can twist the knob and see the servo move around. So with that, I'm going to, whoa, cancel. I almost shut the meeting off. Okay, share screen again. I knew I'd eventually find my slideshow. All right, for homework, we're going to find this. This is very small. It's maybe about a little under ½ an inch in this direction. But it is, it's one of the parts in your kit, and it's called a potentiometer. And this is the knob that you can turn, and the microbit will measure where the knob is turned. What I want you to do as homework is this particular activity. And I'm going to try sending you all this link because I want to make sure that it opens the document and puts the cursor at the right spot. Basically, what you're going to be doing is a portion of the measure potentiometer resistances activity, because a potentiometer is actually a variable resistor. And I kind of wanted you to get some, just with the tutorial, hands-on experience going through and following the instructions, having questions and wanting to ask about them. Please drop me an email if you have a question as you're going through this. And you're going to build your ohm meter circuit that I mentioned, because we'll be using the ohm meter circuit to measure the resistance of the potentiometer. It's going to be really important to use a red, black, red. If you go through that table that I brought up earlier, that's a 2 kilo ohm or 2000 ohm resistor. That's key to getting accurate resistance measurements from your cyberscope. And so like 2.755 kilo ohms. And it'll talk about how a potentiometer works, where it's used. And then of course, we'll be using it for some fun applications on Friday, along with talking about curriculum stuff. Now on the curriculum stuff note, according to Stephanie, the majority of you already have accounts at learn.parallax.com.
Everyone present does. But
Yeah, so in theory, you should be able to follow this link, and I'll email all this to you. You should be able to follow the sign in link and then sign in using your password. Now, if you don't remember your password, there's a nice request new password link here. And then learn.parallax.com will automatically send you a link to follow, it's just like changing your password on any other site. And so then you can use your shiny new password if you don't remember your old one to log in. So just make sure, for those of you who already have access to learn.parallax.com, that you can log in. For those of you, there are 2 of you who have not signed up yet, so we'd like you to sign up. So Stephanie sent you an account activation. And so the heading will look like this, except for it'll have your email name instead of mine. So account activation, your email name at learn.parallax.com, and it'll have the instructions for how to sign up. And so I'd like you to do that, but don't worry if you're having trouble getting in, if for some reason your email administrator is bouncing the emails, you can't find it in your spam queue, you can't find it in your inbox. Don't worry, it's not crucial for completing anything on Friday. It's just important because I want you to be able to get to the resources easily when it's time to do that. So those are the 2 things just so a quick thing, all of this is one chapter. It's just, here's the major chapter heading, here's the parts. So it'll jump you to the same document, but instead of placing the cursor here, it should place the cursor here. So I want to test that. So I'll just send you a link. I'll paste in a link to copy link. So let's see if that works for everybody. Bear with me a second. I'll chat you. Paste. There we go. So try that and let me know if it took you to the parts section of the document. Should be right about there. When you follow the link, we want it to open to, in this case, the parts section.
Mine did.
Awesome. And I'm getting 3 thumbs up for everybody who's not video muted. So if that doesn't work for any of you, just let me know. So I'd like you to try this out. It's going to be a bit advanced. I'm also wanting to go, oh, I see a bunch of people arriving in the dock. Excellent. So for next time, I think I want to start with just a simple voltmeter measurement. You know what? We'll take voltmeter measurements of the potentiometer. And you will have studied how the potentiometer's resistance works. You will have taken quite a number of resistance measurements with the ohm meter that you built and using the cyberscope. And I make sure to bring questions with you. Also, feel free to email me those questions. I'd be happy to answer anything ahead of time. And it also gives me a list of speaking points that may not have otherwise occurred to me. So this will be your homework, is to try a few of the sections here and following along. And then we're going to do some more with the potentiometer, and then we'll start combining the potentiometer with light brightness and servo position. And then lastly, we'll go and take a look at the curriculum resources on learn.parallax.com that are only for you with your Educator login that you're going to verify between now and next session. Okay, how's that, everybody? I kind of feel like I might have gone through that a little bit fast. I'm, looking back, I wish I could have maybe cherry picked a few things to say, well, this is more in general how the thing works, and maybe just said, and here's a list of the topics that are treated with that particular approach. Not sure if it felt at all overwhelming. I apologize for that. I hope it's working okay. If we could get just a little bit of discussion before jumping out for the day. You guys all right? Okay, well, wonderful.
Hey,
all right, then
Andy, can you hear me there?
Yes, I sure can. How's the weather over in Lincoln? It's rather a long ways away from Parallax.
It is. We're a little bit further to the west of you, and we had some pretty strong winds, and so I was sneezing all day yesterday.
Oh.
And I thought I had COVID. I got home. I teach at Lincoln High School, and I thought, oh no, we're coming to the tail end here. Knock on wood. And I thought I had. I got the virus, and so I went to bed early, and I feel like 100%. So anyway,
Okay.
I'm glad you feel better. And I cannot tell you how many times Stephanie and I have started sneezing or had a little postnasal drip, sore throat, and then had to do the swab thing or the.
Yeah, no, it's. I'm just hoping everybody's staying healthy with coming to a close on this. But after taking this, your Cyberbot program with the Python and the microbit, this seems like a good entry level activity or set of activities before taking on the Cyberbot. Are you guys scaffolding this program to run maybe before a Cyberbot microbit activity session, or how does this fit in?
It fits in an either or kind of way. Some classrooms are going to elect to do just this. Other classrooms are going to elect to do just Cyberbot. And then the funny thing is going to be that we're going to get some teachers who want to scaffold Cyberbot on top of this. And then others who who recognize that this is a deeper technical dive and want to actually put it in a later grade. because of the fact that it varies so much, there won't be any official teacher's guide instructions on how to scaffold it one way or the other. I'm really open to suggestions on this, though, and especially Nicole, who does some of the teacher guide stuff, will also want to hear about that. I can either pass it on, or if she's able to join us on Friday, she may hear it directly then. So, but currently, they're just their own little textbooks, and they can be used, concurrently, one after the other, one before the other. But we're presently leaving it at the discretion of each teacher. That was a really good question, by the way. Thank you. Do we have any more questions before we go ahead and stop recording and sign off? All righty. Well, okay, Chris, looks like you're on your way.
I do have one quick question. This is a great track to use Python. Are you going to develop a parallel track for the drag and drop or the make code version?
Yeah. The drag and drop is definitely doable. We know how to do it. The disconnect between the theory that we're presenting here and the drag and drop, there's this is kind of like more oriented towards students who have already been through the drag and drop a certain amount and have been moving their way upwards and are now graduating into text-based languages. At least that's the thinking. Now, during hobby time, I'm very likely to port the Cyberscope module, or pardon me, the multimeter module that we're using now. It's going to be called the Cyberscope module in a little while. I'm very likely to try to port that to the make code blocks programming system so that you could do that. So it's not an official plan, because right now that this is a higher level set of lessons. But another thing is, you can always take just the lessons where you're doing something fun and leave behind the various portions of each chapter that are more theory, because it usually goes, starts at the very easiest and then makes its way to the most challenging near the end. So not yet, but possibly.
Okay, thank you. I like that idea of just taking the first few steps of the module and then doing it, then coming back, and then
especially if you've got middle school students. This is mainly for, the primary audience here is high school. That we're going to see a certain amount of university that are plugging it into, some more higher level stuff. We'll see technical school as well. Then electronics, computer science, electronics, computer science, robotics programs will tend to use it in high school. And then middle school, especially teachers who find their students have kind of plowed through the really easy make code block material and are ready for more. Starting with the earlier activities in a given chapter definitely is a viable approach.
Okay, perfect. Thank you.
Yeah, and thanks for the questions. And Stephanie, would you like to stop the recording? Thanks for coming, everyone. You're welcome to stay a little longer if you like, but